All right, hello everybody. Welcome back to Math Background for Machine Learning. To start with today, I realized from some of the questions last time around that a lot of people hadn't seen Bayes' rule used the way we were using it in the example on Wednesday, the car driving around in a circle with GPS. And so I made another set of lecture notes for people to learn about this way to apply Bayes' rule, and so I figured we'd start by going over those. So the general version of this is called a Bayes filter, and we'll work up to that. But to start out with, let's think about the following situation. We're going to start off with a latent variable, call it x. For example, x could be the GPS coordinates of a robot, which would be a vector in R squared. We'll call x our state vector. Then we start off with a prior distribution on x, and then we get an observation, which we'll call y. And so following the usual convention, capital Y will be the random variable, and little y will be a particular value that random variable could take. And so we'll get the observation that capital Y equals little y. And so that might be, for example, that we observe the readout from a GPS receiver that's on our robot. And so clearly y isn't the same as x, but y provides us useful information about x. And we can summarize that information with what's called the observation likelihood, which is just another name for the conditional distribution of the observation given the state. But in particular, it's this table right here, right? So we've fixed the, right, so without the little y, right, p of capital Y given capital X, this would be a two-dimensional table. And we've fixed the observation to the value that we actually saw. And so this is now a one-dimensional table whose argument is x. And it's called the observation likelihood. And as a reminder, because x is on the right side of the conditioning bar, this doesn't sum to 1 over x, right? This is not a probability distribution. If we had fixed x and we're varying y, that would be a probability distribution. All right, so we started with our prior. We got an observation represented by the observation likelihood. And now we want to calculate our posterior. And to do that, we use Bayes' rule. So the probability of x given y equals y, that's our posterior, is equal to the probability of y equals little y given x times p of x over p of y equals little y. This is just the standard form of Bayes' rule. And I want to point out, we know 2 out of these 3 terms on the right-hand side. We know the observation likelihood, and we know the prior. And so the only thing we don't know is this guy here. And so if we can figure out that guy, we can calculate the posterior, and we'll be done incorporating the observation. And how do we get that? We use the identity that probability distributions have to sum to 1. So let me write that out in a little bit more detail. So we have that, so we have this here, right? Let's unselect that. And so we can write that out. P of x, oops, sorry, P of x given y equals y is equal to P of y equals y given x, P of x over P of y equals y, right? Okay, this here on the left-hand side, that's a conditional probability distribution. So what I'm going to do is I'm going to take the sum over all possible values of x. I'll do that on both sides, and so that maintains the equality. And this here, when we sum over all possible values of x, this is 1, because it's a probability distribution. And so we know that 1 is equal to the sum over possible values of x, p of y equals y given x, p of x. And then what I'm going to do is, instead of dividing by p of y equals y, I'm just going to multiply through. And so that just will get rid of the 1. and we'll put the P of y equals y here. And note that I can multiply through by this because it doesn't depend on x, right? I'm summing over x, but every term has a P of y equals y in it, and so when I multiply through, I get this on the left-hand side. And so what I've just shown is that we can get P of y equals y by doing this summation, right, over all possible values of x. And so we can get this last term here in Bayes' rule, and we can calculate our posterior distribution. All right, so we did that once. Why not do it again? So the process can now repeat. We can receive new evidence, let's say capital Z equals little z, where z is another observation. It could be a very similar observation, right? It could be a second reading from our GPS sensor, but it's going to be an independent new observation. And so we can use Bayes' rule again, right? So here it is written out, right? It's doesn't quite fit sideways, so I'm scrolling back and forth here. And so this is just an application of Bayes' rule. And note that the prior distribution for this application of Bayes' rule, the incoming distribution over x, is exactly the posterior distribution from before, right? It's the thing that we calculated on the left-hand side up here of Bayes' rule. All right, and so we have, just as before, the same two inputs, the prior and the observation likelihood, and we can apply Bayes' rule again in the exact same way, again using the sum rule to calculate the probability of the observation. But there's one more simplification that we will typically make, which is to say that the distribution of the next observation, z, depends only on x and not directly on y, right? It'll depend on y because y tells us something about x and x tells us something about z. But it doesn't depend directly on y. So in symbols, that's P of our observation given x and our previous observation is the same as just P of our observation given x. And if you remember, we ran across an equation like that before, and we called it a conditional independence statement. In particular, we're saying that z is conditionally independent of y given x. All right, and so why do we make this conditional independence assumption? We make it to keep things manageable. In particular, it helps us because this observation table here, P of z given x, the size of that observation table depends only on z and x, and it doesn't depend on our earlier observation. And so if we only have a few observations, that might not matter, but by the time we have 100 observations, we don't want to have to write out a 100-dimensional table of conditional probabilities in order to be able to apply Bayes' rule. Sorry, it'd be 101 dimensions because it would be 100 previous observations plus x. All right, so so that's Bayes' rule being applied repeatedly, right, in a cycle where we keep getting observations and keep updating our distribution over our state variable x. Now, just a word about terminology. The terms prior and posterior, they are relative to a particular application of Bayes' rule. So the distribution of x before we apply Bayes' rule is called the prior, and the one after we apply Bayes' rule is called the posterior. If we apply Bayes' rule a few times, that leads to some ambiguity, because the prior for our first application of Bayes' rule becomes the posterior from our first application of Bayes' rule becomes the prior in our second application. And so prior and posterior, they're very convenient terms, but if there's a danger of confusion, it's a better idea to say exactly what distribution we mean, and I'll try and do that. All right, so just to add a little bit of useful notation, we can keep doing that cycle over and over with, let's say, multiple GPS readings over time. And so it would make sense to have y1, y2, and so forth up to, y capital T if we have capital T of them. And so here, what we're going to assume is that we'll have our initial distribution p of x before seeing any of the y's, and the observation likelihoods for each of the y's. And often, for example, we'll assume that the characteristics of our GPS receiver don't change over time. And so this this conditional distribution doesn't change over time. The only thing that changes is which observation we fill in. Right, so the GPS reading on time 3 won't be the same as the GPS reading on time 2, but the conditional distribution of that GPS reading for each of the possible states, that will stay the same between time 3 and time 2. All right, so we'll just write the same thing that we wrote above. This is an application of Bayes' rule. Our posterior distribution is equal to our prior our prior distribution times our prior distribution here times our observation likelihood divided by the observation probability, which we get as a normalizing factor. And just like before, we've made the simplifying assumption that our observation likelihood depends only on our current state and not on, for example, previous observations. Okay, so our car with a GPS receiver example is one example of where we get this, but this comes up over and over in machine learning. Maybe the most common place it comes up is that our state vector, our latent variable, could be the parameters of some machine learning hypothesis we're trying to learn. For example, it could be the weight vector in a classifier like the perceptron that we were learning before. And then each one of our new bits of evidence could be another training example. So it could be a pair of a feature vector and a true label. And so what we would want to do is repeatedly update our posterior probability over our parameter vector given a new example and the prior, which is the posterior from all of our previous examples. All right, so one last wrinkle to get up to the code that we looked at last lecture, which is transitions. So in the case of a parameter vector, we would typically assume that the parameter vector doesn't change over time. But in the case of a robot with a GPS attached to it, the robot could move. And so we handle that by allowing for what are called transitions, which is to say that instead of one latent variable x, we have a sequence of them, x1, x2, and so forth. And between observations, there's some process that changes x potentially, and we have a conditional probability distribution that tells us what is the probability of xt plus 1 if we knew xt. And just like before, we can apply Bayes' rule to handle an observation. This is the exact same equation as the previous block. But now in between observations, we need to handle the transitions. And to do that, we can use the sum rule. Basically, we can sum over all possible values of the previous state. And this is a way of writing out the joint probability distribution of xt and xt minus 1 given ht, right? This is, if you want to work this out, this comes from the definition of from the chain rule of probability, together with our assumption that xt only depends on xt minus 1 and not ht. So we take the joint distribution over xt and xt minus 1 and we marginalize out xt minus 1, and that gets us the distribution over xt. So we can alternately apply these two processes, apply Bayes' rule to handle an observation, and apply the sum rule to handle a transition. And doing that, we can just keep on updating our distribution over our latent state vector, such as, for example, the position of our car. And that is what the code does, the code example that we handed out last lecture. So hopefully that's helpful. As always, please ask questions on Piazza if anything isn't clear. And let's move back to vector spaces that we were covering before. All right, so we were talking about vector spaces. We went through vector spaces and inner products. Right, so I think we had covered the first two blocks of the set of notes. So basically what they point out is just that Rn isn't the only useful vector space, right? There's a lot of vector spaces where the object in the space, the vectors, are things that are more complicated, like a matrix or a function or something like that. And in order for it to be a vector space, all that we need to be able to do is we need to know how to add and scale or multiply our vectors. And in order to be an inner product space, all we need to do beyond that is to define an inner product that takes two vectors and returns a scalar. So in particular, a really useful example is a vector space of functions. And this is maybe something that a lot of people haven't seen, but it kind of makes sense. And the way that I like to think about it is think about what happens when you plot a function in something like MATLAB or Python. Right, what you'll do is you'll sample the function at a whole bunch of coordinates, and you'll represent the function by the list, the vector, of all of the values of the function at each one of those spaces, right? So, for example, if we have this function here, in order to make a plot, what we would do is we would sample it at, let's say, x equals 1, x equals 2, x equals 3, right, all the way up through, I think we have 8 samples here. And let's say we wrote the value of f, right, the y value, and we collect it all into a vector, right? And so that is what we pass into the plotting program, right? We don't actually, the plotting program doesn't know about cosine x, right? It just knows that x equals 1 corresponds to y equals 1.1, x equals 2 corresponds to y equals 2.0, and so forth. Right, so we just give it a list of the values of the function. And in that way, what we've done is we've taken this function and we've represented it approximately as a vector. And so all we're doing when we talk about functions as vectors in an abstract vector space is we're making that exact. We're imagining sampling the function not just at a few points, but at every possible point, all infinitely many possible points that we could sample it at, and thinking of it as sort of an infinite length vector. And infinite length vectors are maybe a little mind-bending, but they behave just like their ordinary finite dimensional counterpart, right? Like, for example, if you took this function and you multiplied it by 3, well, you would multiply all of the y values in this vector by 3. Right? And if you took two functions and added them together, that would be the same as adding their vectors in the ordinary sense of vector addition in Rn. All right. So, make sure that you understand that when I say a vector, it does not just mean a bunch of like a finite length list of real numbers, the way that many previous classes may have described it, but it means anything that I can add and scale or multiply. Okay. All right, so completeness is the next wrinkle that I want to talk about. So, so we talked about going from a vector space to an inner product space by defining an inner product. For example, the dot product in Rn is, of course, an example of an inner product. But some useful inner products on other vector spaces are given here. So, for example, a useful dot product for matrices is more or less like the dot product for vectors. You just string out the matrices as vectors and you take the dot product of those vectors. And you can write that this way as the trace of x transpose y. A useful inner product for functions is you take the integral of the product of the functions over, let's say, the entire real line. And we'll see other useful inner products for function spaces as well, but that's a good one to keep in mind because, well, it's sort of simple to think about. But the point is that for any given vector space, there's usually many, many different ways to turn it into an inner product space. In other words, there's many different inner products that we could define. So for example, going back to Rn, the usual inner product is just this, the dot product, the sum of the products of corresponding coordinates. But for example, for any fixed matrix A, we can define M equals A transpose A and set our inner product to be X transpose My instead of just X transpose Y. And this turns out to be useful. It's called a Mahalanobis inner product. We won't get into why it's useful, but if you're curious, a useful exercise would be to go and verify that it is in fact a valid inner product. So as a reminder, what does it mean to be valid as an inner product? You need to satisfy sort of all of the usual axioms that dot products satisfy. So that means that it has to be linear in each one of the inputs separately, right? So x1 plus x2 dot y has to be x1 dot y plus x2 dot y. And it has to be symmetric, right? So x dot y equals y dot x. And it has to, right, I listed the axioms up here. Where did I list the axioms? Here they are. X dot x has to equal 0 if and only if x is equal to 0. All right, so that's what it means to be a valid inner product space. As I was saying earlier, the next wrinkle is completeness, which is basically a property about limits. Basically what it means is that we want to be able to take limits of points in our vector space and have that make sense. So in order to take limits, we have to have a notion of distance, and so we'll define our norm based on our dot product, on our inner product, sorry. The norm is just the square root of x inner product with itself. And then we'll just reuse the exact same definitions that you've probably seen for convergence in vector spaces, which is to say that a sequence is a Cauchy sequence if successive points, if the distance between them approaches 0 as you go farther and farther along the sequence. And then convergence, a sequence converges to a point x if the distance from xi to x goes to 0 as you go farther and farther along the sequence. All right. So in particular, I want to point out that it doesn't make sense to talk about convergence until after you have a notion of distance, or you can go slightly weaker than that, but we don't need to worry about that in this course. So you can't talk about convergence in a plane vector space because you need the inner product in order to define the norm, in order to define what it means to converge. Again, you can go slightly weaker than assuming an inner product space, but we don't need to do that in this course. And now once we have an idea of convergence, we can say what it means for a vector space to be complete. It's complete if and only if any Cauchy sequence converges, right? So if we have a sequence of points x1, x2, and so forth in our vector space, there's another point, again, in our vector space that it converges to. And so a complete inner product space, you'll often hear it called a Hilbert space as well, after a famous mathematician, as with many of the things that are named after people. And I'm pointing this out so most of the time we don't have to worry about this, right? So Rn is in fact complete, and so you presumably don't worry about this ever when you talk about Rn. You always know that a Cauchy sequence of vectors in Rn will converge to a vector in Rn. But you have to actually assume that about other vector spaces, and so other inner product spaces. And so, just to give you an idea of how it might fail, a counterexample would be vectors with rational coordinates, right? So we'll call that Qn, where Q is the set of rationals. And in the same way that the set of rationals isn't complete, the vector space Qn is not complete because, so what do I mean by that? We can take a sequence of rational numbers like 3, 3.1, 3.14, and continue that out in such a way that it converges to a real number pi, right? But pi is not a rational number. It's not contained in Q. And so Q is not complete. We have a Cauchy sequence that doesn't converge to any value in Q. And the same thing happens in our vector space. For example, we could have each one of the coordinates being 3, 3.1, 3.14, and so forth. And we would have a Cauchy sequence, and that wouldn't converge into an element of our vector space. But like I said, we're going to usually only deal with vector spaces that are complete, and so we won't have to worry about it. All right, so why have I gone through all the effort of defining abstract vector spaces? It's because it lets us generalize algorithms in a nice way. So what do I mean by that? I mean that we can start with an algorithm that was designed for Rn, and then we can generalize it so that it works on one of these funkier vector spaces. And so we'll be able to, for example, get a if we have a learning algorithm that's designed for, let's say, a perceptron in Rn, where the weight vector is just a real vector of length n, we can use this to make a generalized perceptron where the weight vector is one of these funkier things like a whole function or a matrix or fancier objects. And we'll get to that in a bit. But let's take a look at a specific example which is called a Fisher linear discriminant. And we'll go with Rn first. As a matter of fact, we'll just go with R2 so that we can visualize the plots in an ordinary screen, two-dimensional screen. All right, so here's, you remember we talked before about linear discriminant functions, right? So we have a bunch of points that are x's and a bunch of points that are o's. We're calling the x's the positive class and the o's the negative class, and there's a line that separates them. And this function, right, so the line has an equation w dot x equals b, and so the function w dot x minus b is called the discriminant function because when it's positive versus negative, it discriminates between the two classes. And this particular type of discriminant is a linear discriminant because it's linear. And so we saw one way to build a linear discriminant before, which was the perceptron algorithm. Here's an even simpler way, which is called the Fisher linear discriminant. We take our class boundary, the boundary between the two classes, to be the perpendicular bisector of the line between the class means, right? So let me sketch that, right? So we have a bunch of x's, I'll only draw a few, and a bunch of o's, again, I'll only draw a few. And so the class mean of the x's is right about here, right? And the class mean of the o's is right about here. We can draw a line, a messy line, but a line nonetheless between those two. We can take a perpendicular bisector of the line, which means we go halfway between or of the line segment, I should say. We go halfway between the two endpoints, we draw a perpendicular line like that, and this is our class boundary, right? And so geometrically, that's what it is. In equations, this is what it looks like. I'm not going to go through to convince you that this is the equation for it, but that would be a useful thing to go over on your own because it would make sure that you have some intuition about what vectors in Rn do, how those behave. But we'll just start from these equations for the linear discriminant. And you can see that it actually does a pretty decent job in this very simple case, right? It's maybe the simplest learning algorithm that we have. There are, other ones that vie for that title, but this is certainly a pretty simple learning algorithm. All right, so nonlinear classifiers, right? The linear classifier is fine, but if your data happens to look like this, you're going to be very unhappy with any linear classifier, right? Like, you could put a line right here and it would get all the blue points on one side, but it would have most of the red points on that side too, right? Or a line here, right, and get most of the blue points, but also there's no way to make, it's pretty easy to see, there's no way to make a line that will separate the blue from the red points here. And so what do? What we do is we use a more complicated vector space than just R2. And here, actually, more complicated does not mean very much more complicated. So what we're going to do is we're going to take our two-dimensional points, which we'll call x1, x2, and we'll apply a function phi to each one of them. And so here is a function that maps R2 to R5, right? And so it maps x1, x2 to the vector whose coordinates are x1, x2, the product of x1 and x2, the square of x1 and the square of x2, right? And so now, let's suppose that in R5 we try and learn a linear discriminant, right? That means that we take a vector w that's in R5 and a threshold b that's a real number, and we look at the function w dot our R5 vector, which is phi of x, x being our original vector, so w dot phi of x minus b, right? And so this is not a linear discriminant, at least not in terms of x, but it is a linear discriminant in terms of phi of x, right? So it's a nonlinear mapping from x, which is R2, up to phi of x, which is in R5, followed by a linear mapping from R5 to R. And so if we look at it, if we vary w, right, we can make w dot phi of x minus b be any quadratic function. For example, if we take the last two coordinates of w to be the only things that are non-zero and make them both 1, then w dot phi of x is just x1 squared plus x2 squared, right? And so that's a quadratic function. And so if we can learn a linear discriminant, if we can learn a discriminant function, nonlinear in terms of our original vector, but linear in terms of our expanded vector, then we would be able to solve our classification problem pretty well, it looks like, right? Because we'd be able to learn any quadratic discriminant function. In particular, we'd be able to learn a circle, right? Which we could wrap tightly around the blue points and exclude most of the red points. And in fact, almost the exact same recipe as before still works. We can still learn a Fisher discriminant. And so instead of, if you compare this to the previous set of equations, right, before it was just, the only thing we've done is we've replaced x by phi of x everywhere it appears, right? And so what we're doing here is we're taking the perpendicular bisector between the class means after applying the function phi of x. And if we do that for this particular data set, we get this result here, right? And as I said, that looks pretty darn good. All right, so what did we do? We started with a vector space where we couldn't solve our classification problem, at least not with the algorithm that we had. And we made a mapping to a different vector space where we could solve the classification problem, right? And so that's kind of cool, right? It means we got to reuse a simple algorithm that we had designed for one vector space with a, more complicated, to learn a more complicated classifier by moving to a different vector space. And this particular trick is called a feature transform. It's used all the time in machine learning, right? You may even have seen it before. And it's a really good way to take an algorithm that was designed to learn a linear function and have it learn a nonlinear function. All right, so what I'm going to do next, well, won't completely do it, but I want to talk about it. I want to talk about the idea that our discriminant, that our vector space that we work in for our discriminant function, that vector space can be even more complicated, right? So we moved from R2 to R5. Both of those are examples of Rn, so we didn't make the complexity much higher. But what if instead of learning a parameter vector, we say that our discriminant function itself, right? So f of x equals, but before we had f of x equals w dot phi of x minus b. Let's just forget about w dot phi of x minus b and say that f of x is the thing that we're trying to learn. And we have some vector space whose elements are functions, and we want to directly learn a discriminant function in that vector space. It turns out you can still use the exact same algorithm, which I'll describe how it generalizes in a bit, but you get something that looks like this, right? So here is the class boundary. It is the zero set of a obviously nonlinear function. And this example in particular was learned as a Fisher discriminant. Right. So again, the key thing to get from this set of lecture notes is the idea that vectors don't just have to be lists of real numbers, they can be more complicated objects. And doing that is really useful when we want to learn more complicated objects than just vectors in Rn, like, for example, a whole discriminant function. All right, so I'm going to move on to the next set of lecture notes. This one is called Geometry of Functions. Again, we have, so for today we have a bunch of short lecture notes, so hopefully I'm going to get through multiple sets of lecture notes today. All right, so we have these vector spaces of functions. Before we go too much farther in talking about them, I want to take a detour and talk a little bit about sort of intuition for how to work with functions. And maybe one of the most useful bits of intuition is what's called a contour plot. So if you've seen this before, this is easy, but if you haven't, it's a very useful way to display a function. And there are subroutines in the Python libraries that will let you make contour plots. Same with MATLAB, other standard languages for working with for doing numerical methods. So here is a contour plot. Another way of thinking of a contour plot, another thing you might have seen that's a contour plot before is a topographic map. So what I have here is essentially the inputs to the function are the x and y coordinates, and the outputs, depending on how large, the way we visualize the outputs is by these lines and the color, right? So the curves are called contours, isolines, or level sets. Every one of them is a set of the form x such that f of x equals k for some k in the reals, meaning that our function that we're plotting is the same height everywhere along the contour, right? So it's the same height all along here where I'm drawing, right? And you can read off what that height is by matching with that with the color scale over here. So when k is 0, right, that's the decision boundary. We said before that the decision boundary was when the function switched from positive to negative. And then the other bit of intuition is when the contours are spaced closely together, like they are here, the function is changing rapidly, right? If you go on a hike and a contour map shows you a lot of contours together, you're going to be, you better bring a bunch of water because you're going to be climbing up and down a lot. And then when the contours are farther spaced, the way they are here, it's more level ground. The function is changing more gradually. All right. So contour plots are a useful trick for visualizing functions. Another thing I wanted to mention was geometry of just plain linear function, right? So we looked at linear discriminant functions that look like this, w dot x minus b. So let's just start with b equals 0. So f of x is just w dot x. And we can look at, we want to look at the effect of w on this function. And so to do that, it helps to think about w at least three different ways. One is as a vector in our vector space v, which is equal to Rn, in this R2 in this case. But another is as the linear discriminant function itself, w dot x, and another one is as the decision boundary, right? The surface where w dot x is equal to 0, right? So this plane, or hyperplane, depending on how many dimensions we're in, it's the zero level set of our function f, and the decision boundary of our classifier, and the vector w is the normal vector to this plane, right? So here's what the picture looks like for that in R2. In R3, we would have right, a plane in a two-dimensional plane, and the normal vector would be pointing perpendicular to that plane. And it would still be the zero level set, right? This plane is the set of points where w dot x is equal to 0. And if we make a contour plot, we can see that our vector, it plays yet another role, which is as the direction of steepest increase of the function, right? So if we start here and we want to make the function increase as rapidly as possible, we just go along our vector w. And that direction of steepest increase is also called the gradient of f. Let's see, the length of w doesn't affect the plane at all, but it does change the steepness of this discriminant function. All right, so now let's let our intercept b be something other than 0. In this case, that means that we can shift the plane back and forth so that it doesn't go through the origin, right? So here's an example where the if w dot x minus b equals 0 and b is not 0, then we would have a plane that looks like this black line, right? It doesn't pass through the origin. And here's our normal vector w, right? And so w is still the normal vector, but the intercept b shifts the plane forward and backward along w, depending on how large b is compared to w. So another useful thing to think about is the behavior of the function in the plane when we scale w or b, right? So if we scale w and b together, let's say we multiply both of them by 3, excuse me, that doesn't change the plane. It doesn't change the decision surfaces at all. If w dot x minus b was equal to 0 before, then 3w dot x minus 3b is still equal to 0. But the relative scale, so it doesn't matter to the decision surface, but it does matter, of course, to the steepness of our linear discriminant function. But even for the location of the decision boundary, the relative scale of w and b matters. So for example, if we just scale up b, that's going to move the decision surface farther away from the origin. And if we scale down b, it's going to move it closer to the origin. If we scale w, that has the reverse behavior. If we make w bigger, the plane gets closer to the origin. And if we make w smaller, the plane gets farther from the origin. If we flip the sign of either w or b, that flips the plane to the opposite side of the origin, right? So it will, for example, it would take this plane here and it would move it to about here. And if we flip the signs of both w and b at the same time, that doesn't move the plane at all, but it flips which side is considered a positive example and which side is considered a negative example. All right. So, a lot of people may come in familiar with all of this geometry, but if you're not, it's good to play with a few examples using a plotting program. For example, in MATLAB has nice plotting functions, and Python has nice ones in, there's a library called matplotlib, for example. So, like I said, play with some of these plots, and that should help you have some intuition about the behavior of vectors and linear functions. And as always, if you run into anything you don't understand, post a plot on Piazza and ask us, why the heck does it look like this, and we'll do our best to answer. All right, so we're making good progress today. We have time to go to the next set of lecture notes. We're getting not very many questions today, which I hope means that everybody is understanding everything. We'll go with that assumption until people start asking questions. All right, so vector spaces and dimension. So every vector space has a dimension, although that dimension might be infinite in some cases. Let's work up to a precise definition of what that dimension means, right? And a good example to keep in your head, of course, is Rn. Rn is n-dimensional. But we would like to define more precisely what dimension means so that we can apply the concept to other vector spaces. All right, so let's take a few vectors, x1 through xk, that are in our vector space V, and let's take a few scalars, a1 through ak, and make a vector a1 x1 plus a2 x2, and so forth. And by definition, because addition and scalar multiplication work on vectors, keep them in our vector space, this new vector x, which is the sum of ai xi, that's going to be part a vector in V, and it's called a linear combination of the xi's. And the set of all such x, so keeping x1 through xk fixed and varying a1 through ak for any real values, the set of all such x is called the span of the xi. So the zero vector is always in the span of any set of vectors. For example, we just take the all of the coefficients to be 0, and we get the 0 vector. That might not be the only way to get 0 as part of the span. And that's an interesting distinction. For some sets of vectors, that is the only way to get 0. And for other sets of vectors, it's not. So for example, if you take in R2 these three vectors, 1, 0, 0, 1, and 1, 1, you can get 0 by adding this one plus this one and subtracting that one, right? And so whereas if you just took these two vectors, there would be no other way. If you just take the first two vectors, there's no other way to get 0 other than to set the coefficients of both of them to 0. So if you can get 0 with at least one of the ai being non-zero, that's called a linearly dependent set of vectors. And if you can't, if the only way to get 0 is to set all of the ai to 0, then they're called linearly independent. Order doesn't matter for linear independence, and no vector can be repeated in a linearly independent set of vectors. Otherwise, if we had a repeated vector, we just set the weight on one copy to +1 and the weight on the other copy to -1. And so we'll call the set x1 through xk a linearly independent set. And there are typically tools in a lot of different programming languages to check, at least numerically, whether a set of vectors is linearly independent. For example, MATLAB provides the rank function, and there's a corresponding function. I forget which library it's in, but it's probably called rank in SciPy. And what rank does is it tells us the size of the largest linearly independent subset of our vectors. And so if that largest subset is the whole set, they're linearly independent. And if it's anything smaller, they're linearly dependent. All right. So let's start with a linearly independent set x1 through xk, and consider extending the set by adding another vector xk plus 1. The new vector might allow the set to remain linearly independent, or it might not. It might cause them to become linearly dependent. If it's the case that that our set is currently linearly independent, but every possible vector that we could add to it would cause it to become dependent. In that case, the set is called a basis, and the size of the basis is called the dimension of V. So for example, in Rn, the vector 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, right? The unit vectors, which have a 1 in one coordinate and a 0 in every other, those form a basis. They are a linearly independent set, and if we add any other vector, we can express that vector as a linear combination of the ones that were already there, and so we get a linearly dependent set. And so in Rn, the dimension corresponds to exactly what we are used to having as a notion of dependence. For example, if we're looking at the vector space that we form as the span of two vectors, that's going to be a plane, a two-dimensional set. If we form as the span of one vector, that's going to be a line, a one-dimensional set, right? But it allows us to generalize the concept of dimension to any vector space. In particular, we can get infinite dimensional vector spaces. And those are going to be, it turns out, pretty useful, and so we'll talk about them. So if our independent set, if for any k we can find an independent set of size k, right? So that means we can find arbitrarily many linearly independent vectors. Then we say that the dimension of our vector space is infinite. And a good example of an infinite dimensional vector space is a space of functions. So here's one. Let's take a function called q sub x of y, right? So this is a function of y, and it has one parameter x, and it has this form, e to the x minus y squared over 2. So here's q sub 0, right? And q sub 1 would be the same thing, but shifted so that the highest point is at 1. All right. So now we can form a vector space by taking the span of every such function, right? So meaning that we can take linear combinations of qx1, qx2, up to qxk for any x1 through xk, right? So every element of this vector space is obviously a function because it's a sum of a bunch of functions. And it's well defined, right? Like, you know, you can tell whether you've gotten element of this vector space by seeing whether you can express it this way. So here's an example of a function in the vector space. This is q sub minus 2 minus 1.5 q0 plus 0.75 q1, right? So we took some ones of these functions that are centered at minus 2, at 0, and at 1, and we multiplied each one of them by a scalar and added them together, and we got this, right? So it turns out that this vector space is infinite dimensional. Basically, you can get infinitely many linearly independent functions as part of this vector space. It's not really trivial to prove that fact, and so we won't do that, but it's pretty easy to sort of have a proof by example, right? And I've got a recipe here for choosing a size k set of independent of linearly independent functions. And you can check that recipe for yourself if you like. So that's a nice infinite dimensional vector space. And we can upgrade this vector space of functions now to an inner product space. So we saw an inner product between functions before. The inner product between f and g was the integral over all of r of f of x times g of x. And so we could use that one, but I'm going to take this opportunity to introduce another one that happens to be pretty useful for machine learning. And remember that there are there are infinitely many different inner products that we could introduce on this space. And essentially the difference between them, it's going to change the geometry of the space, right? It's going to change what we consider to be, right? So the inner product between two vectors tells us something about their length and their angle, right? And so if we change the inner product, that means that the same two vectors it will change what we think of as the length or the angle between those vectors. So it changes what we mean by the geometry of the space. And so I'm going to give a definition, and I'm just going to give the definition in terms of a recipe for computing the inner product. You don't necessarily need to understand all of the ramifications of this definition. As a matter of fact, that would be the subject of an entire unit in a class like 601 or 701. And probably like a full course later on if you really wanted to get into it. But the important thing to take away is that there is a recipe that gives you a well-defined inner product that's different from this one, and that we could use in a machine learning algorithm. So we're going to actually follow a fairly standard recipe. What we're going to start by doing is defining the inner product between any two basis vectors. Right, so our basis vectors, if you remember, were functions that look like this, but shifted left or right so that the center point was anywhere in the real line. All right, and so we define the inner product between qx and qy to be qx of y or qy of x. Those are the same thing because these q functions are symmetric, right? And then so I guess the first note is that it's not obvious that this makes sense, that you can use this to define a valid inner product, but it turns out you can prove that, right? And then once we've defined the inner product of basis vectors this way, we can work out the inner product of any pair of functions f and g, because f by definition is a linear combination of the basis vectors, and g is a linear combination of the basis vectors. And so we can use this equation plus the fact that inner products are linear in each argument to work out the dot product. So let me just write that out. So we have, move to a fresh page, we have, suppose that f of x is equal to the sum from I equals 1 to n of ai q sub xi of x, right? So this is expressing f as a linear combination of basis vectors. Same thing with g. G of x is equal to the sum from j equals 1 to m. So m and n don't have to be the same number, right? We're having any finite length linear combination. And we'll call the coefficients here bj, and q sub xj, don't want notation collision, so we'll call them yj of x, right? And then the inner product between f and g is equal to the inner product between sum from I equals 1 to n ai q xi of x, sum from j equals 1 to m bj q yj of x. Right? And then because inner product is linear in the first argument, we can pull the sum outside of the inner product. So this is equal to the sum from I equals 1 to n of ai times the inner product q xi of x. Sorry, that's an x, xi, with the sum from j equals 1 to m bj q yj of x, right? And then again, because it's linear in this argument, we can pull out this sum. So this is equal to the sum from I equals 1 to n of the sum from j equals 1 to m of ai times bj times the inner product qxi of x with, sorry, I should, I apologize for the error. There should be no specific argument here, right? So I'm not evaluating the functions at a specific point. I am just talking about the functions as objects themselves. Apologize for the notation problem. Right, so here in this definition, there's a specific x because I'm evaluating the dot product at a specific point. Sorry, evaluating the function at a specific point. But here the inner product is between the entire function f and the entire function g, right? So f is equal to this linear combination of basis functions. G is equal to that linear combination of basis functions. And then I can pull out the a's and then separately pull out the b's, right? And I get this, q, y, j, right? And then by definition, by assumption, I mean, we can evaluate that, and that is equal to q sub xi of yj. Just a sec. Sorry, in class at the moment.
Oh, okay. That just needs your signature.
Come back during office hours, please. Thank you. Sorry. Was afraid that somebody was coming to tell me about a problem with my video or microphone because that's happened before. All right. So what did I just prove? I just proved that once we've defined the inner product between basis vectors, we can work out the inner product between any arbitrary other vectors, right? So here is a vector, here's a definition of a function f, which is in our vector space, and a definition of a function g, which is in our vector space, and we can work out the inner product between f and g by knowing the inner product between any pair of basis vectors. All right, and so that's the recipe, and I should point out that it's not obvious that the recipe defines a valid inner product, but it does. And if you're interested in the proof, well, there are many higher level machine learning courses that would be glad to teach it to you. The other thing I should mention is that as I've defined it so far, this vector space is not a complete vector space. It does not contain the limit of every Cauchy sequence. And again, that's not obvious, but it's true. And so it is possible to make the vector space complete by adding a few more vectors to it. And I sketched the recipe in this note 2 here, but I'm not going to go over it because that's, again, outside the scope of this course. All right. So that gives us a nice example of an infinite dimensional vector space. What is this vector space good for? Learning nonlinear classifiers, the way I sort of hinted at the end of the last set of lecture notes. So previously, we learned a nonlinear classifier using a feature function, right? So here was the specific function that we used. We computed a nonlinear function of x, phi of x, and we learned a discriminant of the function, a discriminant function that was linear in phi of x, w dot phi of x minus b, right? And here w was a vector in, in R5 to match up with the dimension of phi of x. So what if we say that the feature function of x is q sub x, right? So q sub x is the function we defined up here, like this, right? Shifted so that x is the center. So what we've done now is we've taken our point x, which was in R2, or actually I guess in this case just R1, and we mapped it up to an infinite dimensional vector space. Kind of funky, right? Still a valid feature function, right? It goes from, so the feature function has type R to H, right? Where R is the single real number x, and H is our infinite dimensional vector space of functions, right? So it's a subset of the set of real valued functions of one argument. Right, so again, make sure that you keep your types straight here, right? we're thinking of the output of phi of x as itself a function which can take an input, which is a real, and produce an output, which is a real. All right, so we've transformed x into a feature vector, which is infinite dimensional. It's a function. And now if we can pick a weight vector w, which is part of the same vector space, the same infinite dimensional space of functions, and a real valued threshold b, we can write down a linear discriminant function, w inner product phi of x minus b, right? And so again, this is linear when we think of it as a function in H, our infinite dimensional function space, and it's very nonlinear when we think of it as a function of x. And this is a really flexible discriminant function. In particular, it's going to let us, by choosing w and b appropriately, we're going to be able to approximate any continuous discriminant function on the rails, right? So if we can learn in this space, that's really cool because it means that we have to make essentially no assumptions about what the discriminant function looks like. All we have to do is assume that it's essentially a continuous function, and we'll have a learning algorithm that allows us to learn it. And in particular, we don't have to decide ahead of time whether it should be quadratic, cubic, a mixture of sines and cosines, right, or anything else like that. We just say, okay, whatever nature throws at us, we'll use our learning algorithm and we'll eventually be able to learn it. And interestingly, this exact same learning algorithm that we used before still works. So we can get a infinite dimensional Fisher discriminant function. And that's again defined to be the perpendicular bisector between the class means in this infinite dimensional vector space H. Right, so you saw these equations before where phi of x was a vector in R5. But this same thing actually works when phi of x is one of these infinite dimensional functions. And so, if we apply this to this exact same set of points, here they're two-dimensional instead of one-dimensional because it makes a nicer plot, and we're using this feature function, which is a 2D analog of the feature function that we learned before, we get a discriminant function that looks like this, which you can see does a pretty good job of separating the two classes. All right. And here's like a typical example of a function in our infinite dimensional vector space. This isn't the specific function that we learned here. That one is given by the contour plot from the previous set of lecture notes. This right here, this is the contour plot of the actual function we learned. And this here is a non-contour plot, an ordinary three-dimensional plot of a different sort of typical example of a function in our function space. Right? So here, right, it's e to the x minus y squared, where x minus y squared here is the distance squared between them, and we added an additional parameter sigma squared here. So that parameter, sigma, is called the kernel width, and it influences sort of how wiggly our function is. If sigma is really small, then the wiggles are very tiny and fast, and if sigma is very large, we get a sort of a function with big slow waves in it instead of small wiggles. Okay. So this is sort of a whirlwind tour of infinite dimensional vector spaces and why you should care about them. As a review, infinite dimensional vector spaces are just like finite dimensional vector spaces, except that there's no finite basis for them. There's you can find a linearly independent set of vectors that's arbitrarily large. And so we can make infinite dimensional, maybe the most commonly used example of an infinite dimensional vector space is a vector space whose elements are themselves functions, and we showed how to use that in the context of a Fisher discriminant. All right. let's see, is there time? There's probably time to do a few more examples. So I wanted to give you guys some other examples of infinite dimensional vector spaces to give you sort of an idea of how funky and interesting they can get. And so all of the examples in this set of lecture notes are given in a specific form, the same way we did it before. We're going to write down a bunch of simple elements of the vector space, which we'll call a generating set. And we're going to make our vector space be the span of all of the elements in our generating set, right? So if our generating set was linearly independent, it would then be a basis for the space. Finite and linearly independent. And as a wrinkle, if the generating set is infinite, we will take the completion of the span of the generating set. And again, you don't need to worry about exactly how to do the completion. It's just going to wind up looking like this. That it's going to be, so the span was the set of all finite length linear combinations, and the completion of the span is going to be all infinite length linear combinations with the coefficient where the coefficients are square summable, meaning that the sum of squared coefficients is an actual number instead of being infinite. And we can, maybe I'll skip over this, but we can define an inner product as well in the same way as we did in the last set of lecture notes, by defining the inner product on the generating set and then extending it to the whole space using linearity. All right, so here is the same example that we just saw. So let's skip it because we just did it. Another example that's maybe interesting is strings. So think of all finite length strings over an alphabet sigma, right? So sigma could be, let's say, Unicode characters, or, you know, if you're back in the 1980s, it could be the set of ASCII characters. So vectors are linear combinations of the form 3 times hello plus 5 times world minus 2 times the exclamation point, right? And so it's kind of a little odd to think of a string as a vector, but it's perfectly legitimate to define a vector space this way. As long as we can define, well, so actually we've already defined a vector space just by taking the span of those vectors. And if we define an inner product, we can make an inner product space. And so let's define an inner product to be the inner product of x and y is the number of common substrings in x and y. So for example, the dot product between ard and vark is 4 because there are 4 substrings in common. The string a, the string r, the string ar, and also the empty string, right? Or lolly inner product pop is 2 because they have the string O and the empty string in common. All right, so this seems like a little bit of an odd vector space, but it turns out to be actually a pretty useful one because we can use it for learning text classifiers. So if you think about it, if you want to determine whether an email is spam, it would make sense to look at how many substrings it has in common with known spam emails versus known non-spam emails. We can also make a variant of this by counting substrings with repetition, or by allowing skip substrings, right? So lone.loon would share lone inner product with loon would share the substring lo blank n. We can do the same thing with trees, right? So we can take our generating set to be the set of all binary trees whose nodes are labeled with elements of our alphabet. So here, let's say the alphabet is just three characters that I'll call red, green, and blue. And so here's a tree where the nodes are labeled red, green, or blue. And we can take a vector to be a linear combination of elements of our generating set. So 3 times that tree, that labeled tree, plus 5 times this labeled tree. And just like we defined an inner product on strings by counting common substrings, we can define an inner product on trees by counting common subtrees, right? And so, for example, these two trees share these 6 subtrees. All right, and one last interesting vector space that's maybe of a different form. Let's start with a vector space whose elements are differentiable functions, right? So, for example, we could make it be the space that we defined earlier, because all of those functions are differentiable. And write d to the k for the operator that takes the kth derivative of a function, right? And let's assume that our original space was closed under d to the k. And so then d to the k maps a function in our original space to another function in that space by taking the derivative, or the kth derivative. And it turns out that, in fact, derivative is a linear operator because, for example, the derivative of 3f is the same as 3 times the derivative of f. And so if we take our generating set to be d to the k for k equals 0, 1, 2, and so forth, we can take that to be our generating set, right? And so we can take 3 times the second derivative minus 2 times the first derivative plus 5, where 5 is 5 times the 0th derivative. We get a vector space, and the elements of this vector space are sometimes called differential polynomials. So for example, this differential polynomial turns the function f into 3 times the second derivative of f minus 2 times the first derivative of f plus 5f. And this vector space turns out to be useful for reasoning, for example, about differential equations. For example, if we want to design a feedback controller for a known system. All right, so it looks like we are basically out of time. My office hours start now and run until 3:30. So keep posting us questions on Piazza, and I will see you guys next time around.